All right, today we're diving into a classic lab procedure that honestly is still super important: hemoglobin estimation. We're going to focus specifically on Sahli's method. You might also know it as the acid hematin method. It's a really clever technique that actually turns blood brown to help us measure one of its most vital components. So let's jump right in.
So that's really the big question, right? In a world full of high-tech, automated machines, how does a simple visual test like this one still have a place? Well, understanding Solly's method isn't just a history lesson. It's about getting a real grip on the fundamental principles of hematology. And that's something that's crucial in any lab, especially in places where resources might be limited.
Okay, here's our game plan. First up, we'll get into the core principle, the science behind how it all works. Then we'll check out the specific tools you'll need. After that, we'll walk through the procedure step by step. And to wrap it all up, we'll talk about how to get accurate results, and of course, what those numbers actually mean.
Let's start with the principle. Because before we touch any equipment, it's absolutely essential to understand the clever chemical trick that this entire method is built on. At its heart, Solly's method is all about a simple color change. We take hemoglobin, that's the protein in your red blood cells carrying oxygen, and we use an acid to convert it into this stable brown compound called acid hematin. The key phrase here is visual estimation. This isn't a machine spitting out a number, it's about you matching a color by eye. So this is the core reaction right here. When you mix a blood sample with N/10 hydrochloric acid, which is just a standard dilute solution, that hemoglobin transforms into acid hematin, giving you that brown color. And the logic is pretty simple. The more hemoglobin you started with, the darker that brown solution is going to be.
So how do we actually measure that color? Well, this is the really clever part. The brown solution you've made is put right next to a standardized brown glass comparator. Then you start adding water, drop by drop, diluting your sample until its color is a perfect match for that standard. The final volume you end up with directly tells you the hemoglobin concentration. It's a brilliant, low-tech way to quantify something that's invisible to the naked eye.
Now that we've got the principle down, let's look at the actual equipment. To do this test, you need a specific kit called a Sahli's hemoglobinometer. Let's open it up and see what's inside.
Here are the essential tools. The hemoglobinometer itself is the main housing that holds everything together. Inside, you've got the comparator, with those crucial brown glass standards on either side. In the middle, you'll place the Sahli's graduated tube. That's where the magic happens. You'll use that special hemoglobin pipette to measure exactly 20 microliters of blood. And of course, you'll need your hydrochloric acid, a little glass stirrer, and some distilled water for the dilution step.
All right, time to get hands-on with the procedure. We're going to walk through this together, step by step, from that first drop of acid to getting the final reading. And remember, with a manual test like this one, precision is everything.
Okay, step 1, grab that graduated Sahli's tube and fill it with N10 hydrochloric acid right up to the 2 grams per cent mark. Step 2 is critical. Use the special pipette to drop exactly 20 microliters of blood. Then for step 3, you're going to dispense that blood directly into the acid. Try not to get it on the tube walls, and give it a thorough mix.
And now, you wait. For 10 minutes, just let that tube stand. This part is non-negotiable. It's what allows all the hemoglobin to convert to acid hematin. After those 10 minutes are up, you can start step 5. Carefully add distilled water, drop by drop, mixing after each one until the color of your solution is a perfect match for those brown glass standards. And finally, step 6. You take your reading straight from the scale on the graduated tube. The level of the liquid gives you the hemoglobin concentration in grams per deciliter. Simple as that.
Knowing the steps is one thing, but getting a reliable result? That's the other half of the battle. So let's go over the crucial precautions and some of the common pitfalls that can really make or break the accuracy of this test.
These are pretty much the golden rules. First, always start with clean, dry glassware. You don't want any contamination or weird dilution. When you're drawing up the blood, make sure there are 0 air bubbles in the pipette, because that'll mean you have less than 20 microliters. Lighting is also a big one. Always try to match the colors in good, natural daylight if you can. And finally, be patient when you're diluting. If you add too much water and overshoot that color match, well, you have to start all over again. It's also really important to know the limitations here. The biggest variable is just how subjective it is. I mean, my idea of a perfect color match might be slightly different from yours. That's a huge difference from a modern automated analyzer, which completely removes that human variable. Besides that,
Things like bad pipetting technique, using dirty equipment, or even the presence of certain abnormal hemoglobins can all throw off your results. So, you've done everything right, you've been careful, and now you have your number. Awesome. But what does it actually mean? Let's take a quick look at the normal reference ranges for hemoglobin.
As a general guide, the normal hemoglobin range for adult males is somewhere around 13 to 17 grams per deciliter. For adult females, it's usually a little bit lower, from about 12 to 15. Now you have to keep in mind, these ranges can vary a bit, but a result that's way outside of them is often a signal that more investigation is needed for conditions like anemia or maybe polycythemia. You know, when it comes down to it, Sahli's method is still a cornerstone of lab work for a very good reason. It's simple, it's cost-effective, and it's incredibly valuable in places that don't have all the latest automated equipment. It's a perfect example of elegant, practical science. And that kind of leaves us with a key question. In this age of total automation, what's the enduring power of understanding a procedure not just by pushing a button, but by actually seeing the science happen with your own two eyes?